All right, let's talk about something you probably do almost every day, but maybe haven't thought too much about. We're going to uncover some really cool science hiding in a super simple task.
Okay, picture this. You're in the kitchen, you grab a metal pot, fill it up with some cold water, and pop it on the stove. You crank up the heat. Simple, right? But believe it or not, inside this everyday scene, some pretty amazing physics is about to kick off.
But haven't you ever noticed this? The metal pot gets screaming hot in just a few seconds, but the water inside, it feels like it takes an absolute eternity to even get warm. So what's the deal? This isn't some kind of trick question. It's actually the key to understanding how heat really, truly works. So let's start at the very beginning. The second we turn on that burner, we're pumping in energy, and we can see the effect pretty much right away if we use a thermometer. This is the kind of heat you can actually feel, the kind you can measure. This first type of energy has a great name, sensible heat. And the name says it all, right? It's the heat you can sense because it's directly making the temperature go up. As we pour that energy from the stove into the pot, the water's temperature starts to climb, 20 degrees, 40, 60. That rising number on the thermometer, that is a perfect measurement of sensible heat doing its thing. So here's the puzzle. If both the metal pot and the water are getting hit with the same amount of energy from the stove, why on earth do their temperatures change so differently? The answer is this really important property called specific heat capacity. You can almost think of it like thermal stubbornness. It's basically a measure of how much energy you have to throw at something before it will finally agree to raise its temperature by just 1 degree. And boom! This table just solves our kitchen mystery. Metal has a really low specific heat capacity. It doesn't take much energy at all to make its temperature shoot way up. But water? Water is the complete opposite. It has a super high specific heat capacity. It's basically an incredible energy sponge. It can just soak up a ton of heat before its temperature starts to budge. And that's it. That's why the pot is hot in an instant, but the water takes its sweet time to catch up. Okay, so we've waited, we've been patient, and our water has finally hit that magic number, 100 degrees Celsius. It's bubbling like crazy, steam is pouring out, but now a brand new mystery appears. Yeah, if you were to leave that thermometer in the pot, you'd see something really weird. Even with the burner on full blast, the temperature is just stuck. It's pinned at 100 degrees Celsius, and it refuses to go any higher. So the question is, where is all that extra heat from the stove going? It has to be going somewhere. Well, it's being transformed into something called latent heat. And that word latent is perfect. It literally means hidden, because that's what this is, hidden energy. This energy isn't being used to raise the temperature anymore. No, instead, it's doing the really tough job of physically ripping apart the bonds between water molecules, turning that liquid water into a gas, what we see as steam. It's a change of state, not a change of temperature. And this comparison makes the difference crystal clear. Sensible heat changes the temperature. That's the whole journey from a chilly 20 degrees up to that boiling point of 100. But latent heat, that's what causes the change of state. It's what turns 100-degree water into 100-degree steam. The temperature is identical, but there's a massive amount of hidden energy packed into that steam. So we get the types of heat now, sensible and latent. But how did that heat get from the fiery burner into the water to begin with? I mean, how does it move? To get the full picture, we need to quickly look at the 3 ways heat gets from point A to point B. Pretty much any heat transfer you can think of anywhere in the universe happens in one of just these 3 ways: conduction, convection, or radiation. And the cool part is, our simple pot of water has all 3 happening at once. Okay, let's break them down. First, you've got conduction. That's just heat transfer through direct touch. The hot burner is physically touching the pot, and the energy just jiggles from one molecule to the next. Easy enough. Then there's convection. This happens in fluids, like our water. The water at the bottom of the pot gets hot, it expands and gets less dense, so it rises. The cooler, denser water from the top sinks down to take its place, and you get this rolling current that mixes the heat all around. And finally, you have radiation. This is heat that travels as waves. You don't have to touch the stove to know it's hot, right? You can feel its warmth from across the room. That's radiation. So let's put this all together. It turns out that this super simple, everyday act of boiling water is actually a perfect little model for how heat energy works everywhere, all around us. And there you have it, the entire story in 5 steps. Heat moves from the stove to the pot through conduction.
The water soaks up that energy as sensible heat and its temperature rises. At the boiling point, it switches to absorbing latent heat to turn into steam. And all the while, convection currents are stirring the water and radiation is warming up the whole kitchen.
Now here's the really mind-blowing part. The same properties we just saw are what shape our world. That high specific heat of water that makes your pot so slow to boil, that's the exact same reason our massive oceans can absorb so much of the sun's energy and regulate the entire planet's climate. Those little convection currents in your pot, they're just tiny versions of the enormous weather systems and ocean currents. And that latent heat, the hidden energy that turns water into steam, that is the secret fuel that powers a hurricane. The physics in your kitchen is literally the physics of our planet. Just something to think about the next time you're making a cup of tea.